Hi, in this video we are going to discuss about linear discriminant analysis. It is one of the algorithm where we do dimensionality reduction which is used in machine learning. So just before discussing about LDA, that is linear discriminant analysis, just recall PCA. In PCA what we have done, the main idea is to re-express the available data set to extract the relevant information by reducing the redundant and minimize the noise. So we are going to take, say for instance, 50 features in my data set, and I will be trying to project into the lower dimension space by ignoring the irrelevant information. In the sense, we are not going to ignore all the information, but instead we are going to take all the information, meaningful or necessary information or relevant information, by reducing the redundancy and minimizing the noise. So we didn't care about whether this dataset represents features from one or more classes. That is, discrimination power was not taken into consideration while we were talking about PCA. So in PCA we had a dataset matrix X with dimension, that is m into n, where columns represent different samples here. So if I have x1, x2, x3, so it shows there are three features. So where we can represent a 3 cross 3 matrix. So there are three dimensions. So what we do, we are trying to normalize it, the given data set, and we compute the covariance matrix, and we computed eigenvalue, eigenvector. Then based on the highest eigenvalues, we chose the principal component out of 3, either 1 or 2, which is having highest score. So that is what the final principal component for the given data set, the entire data set. So please keep in mind that say if there are n features are given, say for instance 50, out of 50 it's going to take all the relevant information, say 30, which is meaningful, and from that it will trying to represent in lower dimension space. So this is what we learned from PCA. Now moving on to LDA. LDA is also a dimensionality reduction technique. As the name implies, dimensionality reduction techniques reduces the number of dimensions. If we have 3 cross 3, I will be getting 3 components. Maybe I will be represented in 2 dimension. If I have 2D, then I may be represented in 1 dimension. That is, I am mapping into lower dimension space. So here, say for instance, I have x1, x2. There are data sets are plotted in different colors. So right, so which sees how we plotted relationship between these two variables. If we would like to reduce the number of dimensions, so here what we are seeing here is we plotted 2 features, right? So it represented in 2 dimension space. So now we want to convert into using LDA both the features to create new axis and project the data onto new axis in such a way as to minimize the variance and maximize the distance between the mean of 2 classes. That is what the thing happens in LDA. In PCA, it project onto lower dimension space and maximize the variance. But here it maximize the variance, and also it's trying to maximize the distance between the means of the 2 classes. So here you can notice, say we have x1, x2, the plotted data points, and we draw the line that is the best fit seems to be, and we plotted it onto that line, all the data, and we just simply rotate it so that it becomes as x1. That is the final LD1. So you can see how, but here the line should be in such a way it maximizes the mean of the 2 classes, so that it can be rotated onto x1 axis, so it becomes LD1. So it is most commonly used as dimensionality reduction technique in the pre-processing step for pattern classification and machine learning applications. So the goal is to project a data set onto lower dimension space with good class separability in order to avoid overfitting and also to reduce the computational cost. So initially Ronald A. Fisher formulated the LDA in 1936, and it also has some practical uses as classifier. The original linear discriminant was described for two-class problem, and it was then later generalized as multi-class LDA or multiple discriminant analysis by C.R. Rao in 1948. So if you see the major, it is very similar to PCA, but in addition to finding the component axes that maximize the variance of our data, right? So we are additionally interested in the axis that maximize the separation between two classes. So that is what. So if we have the number of features space, and it will be mapped onto smaller subspace, that is KK, where we represent it, right? So in general, dimensionality reduction does not only help reducing computational cost or a given classification task, but it can also be helpful to avoid overfitting by minimizing error in parameter estimation. So the objective of LDA is to seek reduced dimensionality, as I was saying, and mapping onto lower dimension space. Assume we have the set of d-dimensional samples, that is x1, x2, still xn, that is n1, of which belongs to class w1, and similarly n2 to class w2. So we seek to obtain a scalar y by projecting the samples x onto a line, that is y is equal to w transformation x. So you can see of all the possible lines. So that is what I am saying. So you go with all the possible lines, but it should separate with the maximum distance between two classes. So that is the line that we will select it. Then we rotate so that it becomes the x-axis. So we call that as LD1. So there can be different lines, right? You can form different lines here. You can form different lines, but you should see which line makes the maximum separability of the classes, class 1, class 2. Then you rotate it so it becomes x1 axis. So here it shows the mean vector of each class in x space and y space, how it is given, that is mu I, which is equal to 1 by ni, then summation of x belongs to wi into x, and similarly the mean I of the sub classes can also be computed, and similarly for y space, right? Similarly for the y space, then we go for, that is we compute for x and y space, then we choose the distance between the projected means as our objective function, that is g of w, which is equal to difference between both the means, that is we computed. So these are the general steps for performing LDA. First we compute the mean vector for the different classes from the dataset. Then we compute scatter matrix. Then we sort the eigenvector by decrease eigenvalue and choose k eigenvector with the largest eigenvalue from a d into k dimensional matrix W. Then use d into k eigenvector matrix to transform the sample onto the new subspace. So this can be summarized by the matrix multiplication, that is y is equal to x into w. Let us take an example. Say factory ABC produces very expensive high quality chip rings that their qualities are measured in terms of curvature and diameter. So result of quality control by expert is given in the table below. So this factory ABC, it's already done some of the test based on the curvature and diameter and the result. So all these are some of the test samples in the data set. For instance, there are 7 test samples and out of which first 4 are passed, all remaining are not passed, that means failed during test. So now for example, new chip rings have curvature 2.81 and diameter 5.46. This is my new feature, new data point. For this I want to test whether I want to classify after testing it belongs to passed or not passed class. So this is how we plotted, right? This is how we plotted based on the given data, that is 7 data. This is how we plotted. So your x is equal to, that is features of all data, that is the first row, and y is which is equal to features of all data, that is the column, second column, x and y. And coming to this is how the x is, there are two features, that is the x1 and x2 or xy, and y is the class. The class is represented with values 1 and 2. 1 is passed and first 4 are passed, and remaining all 3 are 2. That means it is not passed. So now what we do is we are trying to find out, we are trying to make it as a group. So group of all passed data set into one group, that is x1, and all 2, right, the not passed into another group, that is x1 is equal to the class 1 and x2 is class 2. This is how we grouped. Now next step is what we are doing is we are trying to find the mean of the each group, that is mu1 and mu2. So how do we find the mean? So adding all the values divided by 4, adding all the values divided by 4. Similarly for x2, adding all the values in column 1 divided by 3, adding all the values in the column 2 divided by 3. So I'll be getting mean of group 1 and group 2, that is mu1 mu2. Then also we compute the global mean vector for the whole data set, that is mu. So what we do is we get the, that is we add the first column of x divided by 7, second column of x divided by 7. So I will be getting this mu, that is for global mean vector for the entire data set. Once this is done, what we do is we are going for finding out the x1 dot and x2 dot. So what I do is I am going to subtract the global mean value with all the values of x1 first column, right? So take 2.88, subtract with all the first column values, and take 2.88, subtract with all the first column of x2, and take 5.67 and subtract the first column of second column of x1 and second column of x2. I will be getting x1 naught and x2 naught. Then what I do is I am trying to find out the covariance matrix. So covariance matrix, I will be getting C1 for x1 naught. So how do I find it? Covariance matrix. So I will be finding out by taking this first column of x1 naught, and that is multiplied again and adding all the values, right, taking first column of x1 naught, multiplying again the same value with that, and divided by 7, right. So divided by 4 here, that is we are trying to find out the covariance matrix of group 1, group 2, that is x1 naught, x2 naught. So taking all the first column, square it each and every value and add it, divided by added divided by 4. I will be getting 0.166. And similarly I take the second column, multiply the square each value, add all the values divided by 4. I will be getting 1.349. And for this covariance of this, what I am doing is taking first column and second column, multiply each and every value, add with other value, that is 0.060 into 0.951 plus minus 0.357 into 2.109 plus multiplying these two value plus multiplying these two value divided by 4. So I will be getting minus 0.192. So this is going to be the same value for this, right? And similarly we do it for x2 naught. I will be getting C2. Now what I do is I am trying to combine these two values to get the covariance matrix of the entire data set. So how do I do is with this equation, that is C of r comma s, which is equal to 1 by n, and n is the total number of data points, and summation of ni into ci of r comma s. So here you can notice that is 4 out of 7 dot, that is multiplied with 0.166 plus 3 by 7, 3 out of 7, 0.259, right? So we are trying to find the covariance of both the groups. I am trying to combine these two. So what I am doing this, so here it is 4 out of 7, right? This is computed 4 out of 7 into 4 out of 7 into 0.166 plus 3 out of 7 into 0.259, right? I will be getting this. And similarly 4 out of 7 minus 0.192 plus 3 out of 7 into minus 0.286, I will be getting minus 0.233. And similarly I do it for the other values. So I am trying to combine C1, C2 like this using this equation. So I will be getting covariance matrix like this. Once this is done, I am trying to do inverse of this. I am trying to take inverse of this. Then I just trying to define the probability vector. What is the probability vector? So probability vector, that is Pi is equal to Ni by total number of data points, that is 7. So out of the probability which is going to be the 1, right? The total value is going to be 1. So the probability which is equal to 4 out of 7 and 3 out of 7. That is how we grouped. So 4 out of 7 which becomes 0.571 and 3 out of 7 which is 0.429. The total is going to be 1. So now use discriminant function. The equation is given like this. So Fi which is equal to mu I C inverse and xk transpose minus 1 by 2 mu I C inverse again mu I transpose plus logarithm of pi. So this is the equation to compute the f1 value and f2 value. So what are the values here? We need to substitute for computing f1 and f2. For instance, if you take the first data point, that is x1, x2, 2.95 and 6.63. So to find out f1, what I do, I take the first data point x1, x2, I take transpose of this in terms of xkt, and already we computed covariance matrix. So that covariance matrix transpose is this, right? And mu I is already we computed mu, that is mean 1, that is mu 1, and mean 2, that is mu 2, already we computed. So substitute value of mu 1 and inverse of covariance matrix and data point transpose, first data point x1, x2 transpose minus 1 by 2 again mean 1 and inverse of covariance matrix, then transpose of mean 1, that is mu 1 plus logarithm of pi. So I will be getting f1. For f2, what I do, again take the same x1, x2 and C inverse, and here mu 2 I will be taking it. Mu 2 I will be taking it for f2 value, right? Mu 2. So only difference is this. So similarly I will be doing for all f1, f2, I will be obtaining all the values. Once I got values of f1, f2, so now using discriminant function, I will be plotting these values. I will be getting like this. This is original data points we plotted, and after finding out f1, f2 through discriminant function, this is what I am getting. Now just simply rotate it, right, to lower dimension space. So what happens here? I will be getting LDA 1. So you can see my new predicted data set like 2.81, 5.46, whether it belongs to class 1 or class 2. I am getting F1, F2 values. If I plot this, I'll be getting somewhere here 44 point something. I'll be getting somewhere here. I can easily say it is classified to non-passed class 2, right? So I hope this makes you very clear in understanding of LDA. And as we were discussing about PCA and versus LDA, so PCA component that maximize the variance and LDA maximize, apart from that, maximize the component access for class separation, right? So this video, it makes you very clear in understanding of LDA. Anything, please do comment. Thank you.